One of the big topics, one of the primary conversations in physics revolves around this word. It's a word you may have heard before. It's a word you may not have heard before. I hope you have. And if not, we're going to figure it out right now. So the word is force or forces. Got lots of them in the universe. 4 fundamental ones. But everything that happens in the universe happens because of forces. Everything. That's weird to think about. One of my favorite kind of crossover science things that I think is so awesome is a field of science called biophysics. Biophysicists are like it blows my mind how cool that is. So I am not a biologist. Like, I did biology in high school, and no offense to anyone who loves it, was not my bag. I didn't enjoy it because I felt like it was just a bunch of memorization. I was like, this is not my deal. Like, physics is where I love that stuff. But like bio, like, okay, so, carbon cycle, blah, 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 Krebs cycle, blah, like whatever. But then I learned about this whole biophysics thing. And so the game is like trying to figure out what makes the muscles pull and push the way they do. That's so cool. And it all comes back to this. It's so crazy cool. Like, let's model how a muscle works to make it, I don't know, awesome. What's a force? Do you know? Star Wars. So in Star Wars, they use the Force. Yes. Now, let's be honest. That's science fiction, right? And I want to make that really clear. I love Star Wars. Like, I love it so much. They use the Force. What do they use the Force to do? Because that's going to help us define this word. What is a force?
Kill people.
Okay, but back up, because you're going from here to here. What do they use the Force to do? It's a simple thing. What does a force do? What? You can use it. You can use the Force to move things, right? Close that door, right? Yeah. Pick up those rocks, right? Absolutely. Let's go into the not fiction realm. What is a force in real life? If you were going to apply a force, what does that mean? Physically.
Apply energy.
Okay, so it's going to be related to energy. Energy is like a whole nother like chapter. Like, we're going to get there. We got to understand this first. So it's related, but let's take it real. Let's simplify. Well, I want as simple as we can go. Yeah.
How things interact with other things.
Ooh, yeah. Okay. So a force is an interaction between objects. That's huge. There, I left a space here intentionally because there's one number that I'm missing, and it's a very specific number. The number is 2. A force is always an interaction between 2 objects. Never between 1, that doesn't, like, between, I don't know what that means. Never between 3 or 4 or 5 or 6. That doesn't mean that 3 or 4 or 5 or 6 things can't interact. But if you're modeling what happens, you have to model it based on each pair of objects. Are you with me there? Okay. So if you're modeling how the solar system works, the Earth pulls on the sun and the sun pulls on the Earth. But there's also that Jupiter thing out there, right? That's affecting things as well. Each of those is an interaction between 2 objects. Awesome. That's one good definition. What else you got? What else is a force? Even simpler. Sometimes people don't want to say it because it seems so simple. If I was going to ask you, Ian, to apply a force, what would you do?
Push.
Push or pull. Boom. Okay? A force is an interaction between 2 objects. The other simple definition is that it's a push or a pull. Boom. That's it. That is it. Okay? A push or a pull applied by one object to another. Okay? If a force is acting, does that mean that an object is moving?
No.
Doesn't have to. Doesn't have to. Yeah. I got my frog. This is my frog. You'll see him a lot today and this year. There's a frog right there. Can you guys see it over there in the corner? Yeah. Okay. I want to know what forces are acting on my frog. What forces are acting on my frog? What'd you say?
Gravity.
Gravity. Is that what you're going to say too? Or are you going to say something else, Rudy?
I was going to say on the table.
And the table. Yeah, so let's write this down. So we're going to draw this frog. You'll draw this frog a number of times this year, so we'll just get started. Get used to it. I am not an artist, but I'm going to draw my frog. I draw my frog as a box with eyes because that seems terribly accurate. It works. Okay? I'm going to draw a picture with all of the forces acting on my frog. Okay? This picture has a very specific name. It's a name that you're going to get to know and get to maybe love. I don't know. Hope so. As we get started. These diagrams are called free body diagrams. Okay? A free body diagram is going to be one object and all of the things that are acting on it. That's all it is. Pretty simple. They get a little complicated, but that is the simple version. So you told me that there were a couple things acting on the frog. Rudy, you said that what was acting on the frog?
Table.
The table. Which way is the table pushing on the frog? Up. Right? So we're going to draw an arrow to represent that force. I'm going to draw an arrow up to represent that force. Now, I am going to be very specific about how I want you to label these arrows, okay? And there is good reason behind it. Sometimes I have people that are very resistant. They're like, I'm just going to draw an arrow and write table. No. I want you to write these very specifically because it's going to help you to get into good habits, and it's also going to help you to process things when we get a couple more chapters down the road. So just trust me is what I'm asking you to do. So we're going to say it's the force. We're going to mark a force with an F. And we're going to say it's the force of he said table, right? The force of the table on the frog. So when you label that arrow, that force, the table is pushing on the frog. It's pushing up. All right. What else is acting on the frog?
Gravity.
Gravity. Now, gravity is a funny one because gravity is the force that you have known about the longest in your life. Okay? When you were 3 months old, you were holding your rattle. This is when you started to get a little bit ornery and your parents were like, oh dear. Right? You were holding that rattle or that little, puppy or that little whatever, and you held it out like this. And then what'd you do?
You put it out your hands.
Maybe before you had a good arm. Before you did that, you let it go, right? You're like, look at that. This is a fun game. And then your parents are like, oh, that's so cute. And they pick it up for you and then they hand it to you again. And then what do you do again? Yeah, right? So from a very early age, all of you have been physicists. You have all been studying the force of gravity, right? You've all been like, whoa, look at that. Whoa, look, it's so exciting. So you've known about this force for a long time. It's ironic because the force of gravity is the one that we understand the least as physicists, like big picture. Like if you ask a real life physicist, which of the forces do we not understand? They're going to tell you gravity. It's the thing we don't get. There are a lot of pieces that don't make sense about it. When we try and fit it all into one nice little neat package, gravity's the thing that doesn't make sense. But for what we're doing, it does. We know that it pulls which way?
Down.
Down. Now, what does down mean?
South.
Who said not up? Okay. We do know it means not up. Where is it really pointing? Where is our arrow really pointing? Towards the, what did you say? Towards the center of the earth, right? Is that what you're going to say too? Center of the earth. So maybe that'll lead us to a clue. Gravity, now this is a funny thing because we'll talk about gravity a lot throughout this year. Gravity is actually a force that exists between any two objects with mass. Any two objects with mass, there's a force of gravity between. Okay? There's a force of gravity between you and your calculator. Okay? It's an attractive force. Okay? But that's not the one we usually talk about. When we're talking about Earth and we're talking about that little pacifier or rattle or puppy or whatever that you were holding out when you were 3 months old and you let it go, what was it that was pulling on that object? No, what was it? Because remember, we're talking about an interaction between two objects. So if we're talking about your pacifier, right, you're holding your little pacifier out there, you're like, ha, 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 right? There's an interaction between your pacifier and what that made it fall? The earth. Are you with me there? It's the earth that was pulling on your pacifier. It wasn't gravity. Gravity is not a thing that you can, it's not an object. You don't walk into Ace Hardware and say, hi, I'd like some gravity, please, right? Like, it's not something that you can, like, physically hold, right? I need it to be an object. The object in this case is the earth. So you're going to say it's the force of the earth on the frog. Is that okay? Awesome. Now, there are some little details in here, some of which we'll work out later. But based on your intuition, and based on you looking at the frog that's sitting on the front table, tell me about these two forces. What do you think these two forces have to add up to?
0.
Why are you saying 0?
One's greater than the other. I'll go that way.
Because if one's bigger than the other, it's going to go somewhere, right? And what did you say? It's not what?
What did you say, Harry?
You said something.
It's
not
moving.
It's not moving. Yeah. So we know that the magnitude, and magnitude is a key thing there, right? That the magnitude of the force of the table on the earth, or excuse me, on the frog, is equal to the magnitude of the force of the earth on the frog. Okay? We know that their sizes are the same. Tell me about their directions, ladies and gentlemen. They are opposites. How do you know that they're opposites? Well, because their picture says so, right? So I'm going to put a little negative sign in front of one so that I can keep track of the fact that they are opposites. Bless you, bless you.
You've been blessed.
Okay? Goodness gracious.
Stop, Steve.
Okay. How are we doing? Are we okay? So we can also say that these add up, or we can write it as the net force. Have you heard the word net before? Netflix, not the right net. Net force. You may know what that means? Total. Has to equal 0. What's that? The frog is in fact deforming the table. The frog is certainly deforming the table. But once the table is, now he is not accelerating anywhere. He's not going anywhere, right? So when I set him down, he went, not very much, like we can't see it, but he totally is deforming the table. If he wasn't, he'd have no mass, and then we wouldn't be talking about this story. How are we doing? Are we okay? All right. So we're going to talk about these forces a little bit more, but we're going to talk about them with some other specifics. I've got a few problems. We're not going to get through all of them today, but we'll get through some of them, and we're going to define some terms here. So we're going to draw lots of these pictures. Is really what I was going to say. All right. This is really little. You can't read that in the back. Hello. Wow. All right. I love this set of problems. It comes from an old textbook that I had. I love it because it's got this whole mystery box. So a friend has given you a special gift. It's a box. Here's a box. It's 10 kilograms in mass. It can be whatever you want as long as it's 10 kilograms. It could be a kitty, or it could be M&Ms, or it could be anything you want.
If your cat weighs 10 kilos,
That'd be a lot of M&Ms. Would it be great? I would accept that gift. All right. The box is resting on a horizontal surface of a table. It says determine the weight of the box and the normal force exerted by the table. Whoa! Those are some words that we have not yet talked about. Now, you may have heard of those words before, but you may also not have. So let's get it figured out. There's a lot of things here. I don't want you to worry about reading any more on there. I just want you to read some words here. We're going to read them and we're going to write them down. Now, you know that I'm going to put all this stuff up online, right? So you don't need to copy these down. If you want to write this down, which I would label this mystery box number 1. Because if you look over here, we're going to have mystery box number 2 and number 3 and number 4. So we'll have a few mystery boxes. Because like I said, I like this book because it has lots of these and they're really good. They kind of build on each other. All right. So we're going to define some words here. The first one is the word weight. Oh dear, here we go. We're jumping in with both feet today. Weight is not a word that I will use frequently at all, pretty much ever, except for today. Because the word weight I find to be a little bit confusing, and I feel like I can be a little bit more specific. But what is your weight? What does that mean physically? Go.
The effect of gravity on you, basically.
Yeah. Your weight is really, stop, silly thing. It's really the force of gravity. You guys know how I feel about that already. So really, it's the force of the earth on an object. So now we're translating this into good physics lingo. Your weight is the force of the earth or whatever planet you're on, okay, on the object. That means that your weight can change. Okay? How do you measure your weight?
Scale.
Right, like a bathroom scale, right? You put it on the floor, you step on it, now you know your weight. Okay? Really, what is it doing? It's pushing back up on you the same as you're pushing down on it. Are you with me there? Kind of like with the frog.
Whoa.
Okay? That's really literally what's happening. So if you have an opportunity to go to the moon, in your bag that you get to take with you, take a bathroom scale. You take that bathroom scale, you get onto the surface of the moon, right? You're not going to be like, one giant leap for blah, blah. You're going to be like, let me get my bathroom scale out. And you're going to put it on the surface of the moon. You're going to stand on it and be like, I just lost a lot of weight. Now, usually when people say that they lost weight, what are they really talking about?
They're losing force.
They're losing mass, right? If you lose weight, really, generally what you're talking about is that you're losing mass, right? You gain weight, you gain mass. But the more mass you have, the more weight you have. You with me there? But if you literally are talking about gaining or losing weight, you can go to a different planet, or you don't have to go to a different planet. You go up to the tip top of Mount Everest. You go way up high. The force of gravity, the force of the earth acting on you way up there is different than it is here. It's less. So when you go on your expedition to the top of Mount Everest, right, and you get this one bag that you get to schlep up the mountain, what are you going to make sure to put in that bag? Your bathroom scale, right? You pick that bathroom scale up, you get to the top, you're like, I don't need to look at the views. Get my bathroom scale out, step on it. I lost a lot of weight. No, not mass. Now, in training for that trek, you may have lost mass. Although most of us don't need to lose, we wouldn't want to, we'd be wasting away, and that's not good, right? But the actual measurement of your weight would be different. You go on a trek down to Death Valley. You got your one backpack to schlep all the way down there. Okay? You're not like, wow, it's hot when you get there. You're not like, let me take a break. You say, let me get out my... You guys get it? You take your bathroom skill out, you stand on it. Wow, I've gained weight. I'm sitting here sweating and I've gained weight. Because it's changing the force of the earth on you. Are you with me here? Is this making sense? Okay? The force of the earth, the force of gravity, weight, is dependent on two things. I'm going to write it as F sub G, and I'll explain to you how this is all going to work in a minute. But I'm going to write it as F sub G is equal to your mass, or the mass of whatever object it is, times this little g. Now, I don't know where you all have existed in science prior. If you took foundations, you may have seen this 5 million years ago when you did it, okay? So I'm going to assume that you don't know this, and if you do, that's fantastic. You with me there? I just want to make sure that we're all on the same page. This M, we just maybe said, maybe I said it out loud, I can't remember, stands for mass. This little g, we're going to get to know, we're going to love it, we're going to measure it. It's going to be great. Little g is the acceleration due to gravity and so usually we talk about it as on the surface of Earth. Okay? G can be the acceleration due to gravity on the surface of Mars. Okay? It doesn't have to be on Earth. I just want to make that clear. And the value that we use for that is equal to, does anybody know? Oh, look at these little mumbles. I love it. Negative 9.81 meters per second squared. We have not mentioned the word acceleration until just now. Woo! That's okay. For now, I just want you to have that in your brain and be willing to multiply for me. Because everything that we're doing in Unit 1 up through the rest of this week, we're not going to mention that A word anymore. Okay? This one right here. We're not going to mention it. We will get to know it. We will get to love it, but not yet. Okay? Because I want you to just understand this constant velocity business first. Okay? So we're going to write this down. You're going to remember that, and I'll give you an equation sheet that has it on there very soon. Okay? But you're going to know that, and you're going to love it. Questions so far? Okay. We can answer the question now. We can determine the weight of the box. Probably you don't need a calculator. In fact, I hope you don't need a calculator. But I want you to determine the weight of that box. Can you do that for me? Yes, Miss Carmine, no problem. I'm right on that. How do you do it? I want to know the weight or the force of gravity or the force of the earth acting on the box. Talk to your table mates. What's the answer? Can you do it? I don't know. How do I find the force of gravity? What does the equation right here say? The mass times 9.81. What's the mass? I have 10 kilograms of kitties. I have 10 kilograms of M&Ms. I have 10 kilograms of something I don't know. It's a mystery. Right? I've got 10 kilograms times 9.81. I can multiply by 10 pretty darn easily, right? What is it? Say it, come on.
90.
Yeah, there you go. So part A, the weight is really, I'm going to write as FG is equal to 98 0.1, and then we have to figure out what this thing is measured in. What? Mass is in kilograms. This crazy acceleration business is in meters per second squared. That is a lot of goofiness to write down. That is a lot of goofiness to write down right there. Anybody have a suggestion instead of writing a kilogram meter per second squared? What do I want to call that? Kilograms times meters is something, but I want to make my life even better. Niam, you want to make my life even better? She wants to call it a Newton. Now, Niam has the unique feature to know that I strongly, strongly dislike the gentleman for whom this unit is named. I have very strong feelings about that, and that'll come up another day because we don't have time for that today. But regardless, I don't feel like I should make you guys buck the trend and like come up with another unit name. Like that just seems a little bit, it doesn't seem very, what do I say? Useful. So we're going to call it 98.1. We're going to call it a Newton. It's marked with an N after the gentleman who takes lots of credit for lots of motion things and who I'm not a fan of, Sir Isaac Newton. He's a bad guy. Not a fan. We'll get there another day. Not right this moment. All right. So if you want to write this down, and not even if, I would encourage you to write this down. Maybe right over here, we're just going to say that 1 Newton equals 1 kilogram meter per second squared. That's really just making your life easier. So you don't have to waste as much graphite writing it down. Okay? How are we doing? We okay? Yeah.
Should it be negative 98.1?
That's an awesome question. I'm so glad you asked. I was hoping somebody would say something about that negative sign. What's up with this negative sign? What's up with no negative sign here? Okay, so here's the game.
The name of the game.
Which way does that force push or pull?
Down.
Down. The force due to gravity always pushes down. That's why this is negative. This is why I don't like the word weight. Because weight just sounds like, it's not like you're going to say, I weigh negative 30 newtons. That would imply that you have less than, you know what I'm saying? So the negative really just means downward. So when they ask for the weight, I'm just going to leave it at 98.1. If they said, what is the force due to the earth? I would say it's 98.1 down or negative 98.1. Does that make sense? Is that okay? But I'm super glad you asked that because the negatives, I sometimes get lazy with negative signs. And so I hope that you guys will kind of call me on that so that we can keep it consistent. Okay? All right. We're going to power through to get done with part A. Here we go. We're not quite done. Got another big one. Here it comes. Part A, we're only halfway done. It says determine the weight of the box and the what? The normal force? Like what is that? Right? I think this is the force that has the strangest name unless you think about it mathematically. If you think about it mathematically, it makes total sense. Please stop fighting with your pencils. Thank you. Okay. Let's talk about the normal force. Let's do it real quick. Here we go. Normal force. If you ask a random person out on the street, what does the word normal mean? They're going to say what? Regular? Unexciting? Something like that? Turn your mathematics hats on for just a moment, especially my pre-calc and calc friends. What does the word normal mean in mathematics? Does anybody know?
Not a math.
Close. I will tell you, let me give you a hint, maybe this is a hint, I don't know, that a radius is always normal to the tangent line of a circle. What does that mean? If I have a circle, bring those geometry brains back. Here's the radius. Where does the tangent go? Oh, what did you say? Perpendicular. Yeah! Ding, 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 ding. We win. All right. The word normal in mathematics and physics means perpendicular. It means perpendicular. A normal force is always perpendicular to a surface. Okay? It's the surface acting on an object. So the normal force, I often write F sub n, is really the force of a surface on an object. How are we doing? Are we okay so far? So in our little frog example, this was a gravitational force. The table on the frog is really a what? It's a normal force. Is that okay? If you draw the table in there, which we totally could do, this force is always perpendicular to the surface. So I'm going to write in here real quick on my froggy thing. I'm going to write this as F sub n. I'm going to write this one as F sub g. And then I'm going to go one more thing, but I got 1 more minute. Oh my gosh, holy cow. I want to know how big is the normal force acting on that box. Can you tell me? If the box is sitting on a table, it's not moving. It's going to be 98.1, isn't it? Going which way? Up. So should it be negative? Well, technically this one is the one that's negative because it's going down towards the center of the earth. Are you with me there? Yeah? All right. I'm going to write that down. The bell's going to ring in just a second. I'm going to say thank you guys so much for paying great attention today. We'll start here tomorrow. Isn't it? Yeah, there it is. Boom.